Hello everyone, I am Daniel Lysenko, the leader of the EN4 Fluid Mechanics group. This year, the goal is to empty a 6-liter bottle through a 10mm hole as fast as we can. In this video, I will take you through all the process that we have encountered from the calculations to the design, manufacturing and testing, and we'll show you our result times. Thank you.
First, we will obtain the nozzle geometry function. The transition function is a fifth-order polynomial that smoothly transitions from one desired radius to another. The main goal is to obtain A, B, and C to achieve several constraints. We want to have the radials at 0 equal rho r1 and at L equal to r2. Also want to have the slope at 0 and L equal to 0. First, we try to minimize the time function that is proportional to the transition function. Using a MATLAB numerical method function, we obtain the values for A, B, and C. In this case, the function appears to be convergent-divergent, and we do not want that, since our fluid is non-compressible. Therefore, we decided to minimize the pressure losses which come from the Hagen-Poiseuille function, and introduce a monotonic constraint which makes the function only convergent. From this, we obtained values for A, B, and C, which result in a realistic nozzle. This MATLAB numerical method script shows us the iterative process we take to obtain the desired constants. This other function creates the desired plots from the function that we give it. This MATLAB function creates a CSV file containing a series of points representing our transition function, which we will later upload to a design software. To predict the drainage time of our bottle, we begin by applying the mass conservation equation to our control volume. The bottom hole is considered static, while the upper water surface moves as the volume decreases. Assuming water is incompressible, we derive an expression that links the change in water level to the outlet velocity and certain constants. Next, we assume an ideal scenario with no energy losses, allowing us to apply Bernoulli's equation along a streamline from the top surface to the outlet. A key assumption here is that pressure inside the bottle remains constant and equal to atmospheric pressure. Combining both approaches, we derive a differential equation that relates water height to time, and solving it gives us the total drainage time. When plotting this time against the diameter of the air intake, we observe that larger diameters actually increase the emptying time due to reduced water flow rate. However, the Reynolds number graph reveals that the airflow is not laminar. This, combined with the high air velocity, challenges our no energy loss assumption and suggests that internal pressure may not remain atmospheric, particularly at the start of the process. Using this MATLAB software, we calculated theoretical drainage times and plotted graphs showing water speed, Reynolds number, and drainage times as functions of the air intake diameter. The generated transfer function was exported to Fusion 360 computer-aided design software to create the axisymmetric nozzle shape. Additionally, a groove was implemented in order to use an O-ring, preventing possible leaks. A critical element of our design is the pipe for pressure equalization, which will reach out of the cap at the edge of the outlet hole. We have designed two prototypes with different diameter of the tube. We can observe in the first image that the tube is 2 mm in diameter, whereas in the next image it is 3 mm in diameter. We want to test if the air intake tube diameter will affect the drainage time, and if a bigger tube is needed to avoid chalking the bottle. The CFD simulation allows us to visualize and analyze the behavior of the fluid inside the nozzle. Simulating the flow helps us understand how the fluid speeds up, how pressure changes along the nozzle, where turbulence might appear. In our case, we perform simulations both with and without the nozzle. The results show that the presence of the nozzle leads to a smoother and more controlled flow, minimizing turbulence and ensuring a more stable drainage process. After modeling, we chose a manufacturing method that could precisely replicate our calculated profile. 3D printing was the ideal option, with resin printing offering higher resolution than FDM. Its precision allowed us to include an internal duct for air pressure equalization without concerns about overhangs. It also provided a smoother surface finish, though this has little effect in laminar flows. Our final design includes a tube connected via a 6 mm pneumatic fitting to reduce the air spring effect. In these photos, you can observe the final pieces. We glued the bottle tab to the fittings, so it is possible to fill the bottle with water without any problem. The final pieces turned out to be of excellent quality. We'd like to give a shout out to imprimakers.com for quickly printing the nozzle and delivering great results. As mentioned, the pneumatic connector and tube will run up to the top of the bottle to equalize the internal pressure with the ambient pressure. A big thank you to Mercadona for sponsoring this video. They provided us with a Broncalis bottle, which served as the container featured in the project. This video wouldn't have been possible without their support. Now back to the video. We conducted 3 drainage tests. The first clip shows the drainage time using the initial nozzle, which features a 3 mm diameter air intake. This experiment confirmed that sufficient air was entering the bottle through the tube, as the bottle did not compress during the process. The total drainage time with this fitting was 1 minute and 53 seconds, which, when compared to the theoretical time of 60.73 seconds, resulted in an efficiency of 53.74%. Next, we tested the nozzle with a 2 mm diameter air intake hole. We observed that, even with this smaller diameter, a sufficient amount of air was still entering the bottle, as it did not show any signs of compression. Using this nozzle, we recorded a total drainage time of 1 minute and 51 seconds, which is quite similar to the result obtained with the 3 mm diameter air intake. This suggests that the size of the air intake hole does not significantly affect the overall drainage time. Based on our calculations, the theoretical drainage time was 57.57 seconds, resulting in an efficiency of 51.86% for this nozzle. Lastly, we tested the drainage time through the 10 mm hole, but without any nozzle or pressure equalizing tube. This test was conducted to verify whether our fitting was actually necessary to improve drainage performance. We observed that the total drainage time for this setup was nearly 3 minutes. The absence of pressure equalization caused significant compression of the container and introduced uncontrolled bubbling into the system. In comparison to the nozzle setups, which drained in approximately 1 minute and 50 seconds, this configuration was about 1 minute and 10 seconds slower, demonstrating the clear advantage of using the pressure equalizing fitting. To further improve our experiment and refine system performance, several additional steps could have been taken. Conducting more tests under controlled conditions would have provided more reliable data and helped identify which nozzle design consistently performs best. Iterative testing could also have optimized the nozzle shape, tweaking diameter, length, edge sharpness, or angle for more efficient flow. We could have explored different materials with smoother surfaces or lower friction to reduce energy losses, and used more precise manufacturing tools to improve part fit and minimize leakage. Another variable worth testing is water viscosity, which directly affects flow resistance. Slightly heating the water or mixing it with a low viscosity liquid could improve discharge efficiency. These improvements would have enhanced our understanding of the fluid dynamics involved and potentially boosted overall system performance while staying within the experiment's constraints. This table summarizes our experimental drainage times with theoretical predictions for different container configurations. With a 3 mm air intake, the container drained in 113 seconds, nearly twice as long as the predicted 60.73 seconds. The 2 mm intake performed similarly at 110 seconds versus a theoretical 57.57 seconds. Without any nozzle, drainage was slowest at 180 seconds. Efficiency shows how close we got to a near-best performance. Both intakes achieved about 53% of efficiency, which is obtained by the quotient between the real time by the theoretical one. These results suggest our system experiences substantial flow restrictions, likely from factors like surface tension or air intake limitations. The similar performance between 2 mm and 3 mm intakes implies we may be hitting a minimum drainage time threshold for this setup. We hope you found this video both informative and enjoyable. Thanks for watching.